Hello everyone, and welcome to the second lecture of the Bio 103 series. This lecture will be on biological chemistry, so it will be an overview of the chemical principles that underlie the characteristics of life. So although they're two distinct sciences, there is a lot of overlap between biology and chemistry. So there's a few definitions that's important for you to know. The first one is matter. Matter is defined as anything that takes up space. So the pen in your hand would be considered a substance that has matter. However, mass is considered to be the measure of the actual amount of matter. So there are two completely different terms referring to two different properties. Weight is often a definition that gets confused with mass, but weight is defined as the actual force of gravity that is pulling on that matter. So mass is considered to be constant no matter what type of environment you are because it's based on the amount of matter present. However, weight will change depending on the force of gravity. So for instance, if you are measuring your weight on Earth, this would differ if you were to measure your weight on the moon because the force of gravity is much different and non-existent on the moon. An element is defined as a pure substance made up of one type of atom. An element cannot be broken down, even by any chemical reaction. So these elements can be represented in the periodic table. We have 92 naturally occurring elements. 25 are considered to be essential to life. And they comprise 96 of the biomass on Earth is comprised of these four important elements: oxygen, carbon, hydrogen, and nitrogen. A compound, on the other hand, is when you take two or more different elements and you chemically combine them together. A compound exists in a fixed ratio, so anytime that you change that ratio, you are creating a new substance, a new compound with new physical properties and chemical properties. So here are some common elements that are found in nature. We have sodium here. This is in its elemental base form. We also have chlorine. Now what happens when you create a compound and join these two elements together? You get what is termed sodium chloride, and this is your typical salt. So if you know anything about the salt manufacturing business and salt production, a common term that you will find if you take a look at salt containers is you will see that it actually terms it as iodized salt. And so that means that during the manufacturing process, they add iodine to the compound, and this helps to preserve it. So why this becomes important is when we have developing countries or impoverished countries, they do not have a lot of processed foods in their diet. As a result, they might be lacking iodine intake, or they may have insufficient iodine intake. And this can lead to a typical illness seen here, which is termed goiters. So if you have insufficient iodine intake, you get swollen thyroid glands, which leads to the formation of a goiter as seen here. So we do not have this issue in North America, and this is because of the salt manufacturing and the iodine that is added to it. There is so much salt content in many of our foods that we buy that are pre-processed, and as a result, we are constantly getting iodine in our diet, so we are hardly ever insufficient in iron with respect to our diet. So let's take a look at atomic structure. So you should be familiar with how an atom is structured. The properties of a substance are based on the atomic structure. Specifically, we're going to be looking at the importance of the electrons and their configuration and how that plays a role in how atoms bind together. So an important definition that you should be familiar with is what is an atom. So an atom is considered to be the smallest unit of matter that still retains all of those properties of the element itself. If we take a look at the atom, we can divide it up into different subatomic particles. A proton is considered to have a positive charge, and it has an average mass of 1 Dalton. You may also see in the text or in various sources AMU, which refers to atomic mass unit. Dalton and atomic mass unit are interchangeable and considered to be equivalent. A neutron has neutral charge or no charge, it also has a mass of 1 Dalton. And then the final subatomic particle is the electron, and the electron has a negative charge and its mass is negligible. So what's important to note about these particles is 1, what type of charge it has, and 2, the relative mass of these subatomic particles. So if you look at how these are arranged in space to form an atom, the protons and neutrons aggregate together to form the nucleus as seen in the image here. The electrons orbit around the nucleus, much like a solar system. So when you are looking at atomic structure and the information provided in, say, the periodic table, there's some important information that you should know. The first one is atomic number. So atomic number refers to the number of protons. So here we've got an example in helium. It's got an atomic number of 2. And that means that it would have 2 protons inside of the nucleus. The mass number refers to the number of protons and the number of neutrons. And the reason for this is because if you consider the relative mass of all of those subatomic particles, the electron doesn't contribute much to the mass of an atom. It's the proton and the neutron that contribute to the mass because they have a mass of approximately 1 Dalton each. So if you take a look at the mass number, that would give you an indication of how many protons and how many neutrons are present. So once again, if we take a look at helium, we see a mass number of 4, and that indicates that there would be 2 protons from the atomic number, and you can use that information to figure out how many neutrons there would be. 4 minus 2 is 2, so there would be 2 neutrons in the helium atom. Isotopes are considered to be different atomic forms of an element that contain different number of neutrons. So that means the proton number remains consistent between the atom and the isotope. However, the mass is going to be different because if you remember, neutrons carry a weight of 1 Dalton each. The physical and chemical properties of the isotope and the base element remain the same, so these isotopes are going to react very similarly. And as the isotopes get heavier, they do become more radioactive. So the more neutrons you add to the nucleus, the more you increase the radioactivity of the isotope itself. So here are some common examples. Here are 3 examples of hydrogen. You can have elemental hydrogen. If you add a neutron, you form deuterium, and if you add 2 neutrons, you form tritium. You can use this radioactively labeled or isotope hydrogen to create what is termed heavy water. So heavy water is when you have deuterium in the compound or in the water molecule instead of your typical hydrogen. This can be very helpful in tracing water molecules and tracking their movement between cells or within cells. You can also have different isotopes of carbon. So carbon-12 is the regular carbon that we are familiar with. It comprises over 99% of the carbon on Earth. However, there are 2 other isotope forms that are available, carbon-13 and carbon-14. If you look in the literature, you might see radioactively labeled isotopes sometimes get an asterisk next to their element symbol, and this would indicate that you are in fact dealing with an isotope. So please be aware of that notation. Isotopes can be very helpful and very useful in many different ways. So as I stated before, in looking at heavy water and its use, you can mark certain molecules by using these radioactive isotopes. And this will allow you to trace where these molecules move in systems and also within a cell or within an organism. You can use it to highlight certain areas, so it's very useful in diagnostic imaging. And you can highlight or radioactively label certain compounds that you know have a higher uptake in a certain tissue. And as a result, you can isolate that tissue, and then that can be very useful in diagnosing tumors, for instance, and other metabolic disorders. This can also be paired with various types of therapy. So if you can highlight a certain tissue, like a tumor tissue, you can direct the treatment protocol to that specific tissue. So instead of treating a whole entire body with radioactive chemotherapy, or radioactive therapy, you can direct it specifically to the tumor tissue so that you are minimizing the damage and minimizing any side effects towards the patient. So this slide goes over that electron configuration. What's important to know is where the electrons lie, how many electrons are in what we term the different orbitals, and what happens when these electrons go between different orbitals, because they can jump from one orbital to the next. So if we look at the atom and how it reacts to each other, an atom's chemical properties are due to its configuration of its electrons, specifically how those electrons are arranged in space and how many electrons are in the outermost shell or the outermost orbital. We call that outermost orbital the valence shell. The electrons that reside in that shell are termed the valence electrons. And so these valence electrons are basically what determines the properties and reactivity potential of those atoms. Energy is defined as the ability to do work. Things tend to flow from a high or unstable energy state to a lower stable energy state. And that is important because if we take a look at how these electrons can bounce between the shells, if they are going from a higher to a lower shell, they're going to be releasing energy as they do so. If an electron is going from a lower shell to a higher shell, it's going to require energy input in order to move to a higher orbital. The number of electrons that are contained in an orbital is very important. So for the first electron shell that resides right outside of the nucleus, it has a very small capacity because there's not much room there. So that means it can only hold 2 electrons maximum. The second electron shell can hold up to 8 electrons. And if you take on further chemistry, you will get into different orbitals and different number of electrons that can be residing in those orbitals. But I will state, for the purposes of this course, we kind of cap it out at 8 electrons. So even though the third electron shell can contain many different electrons, we only consider it to be filled to 8. So it can only hold a maximum of 8 electrons. Remember that atoms like to have their valence shell filled, whether it's 2 in the first orbital or whether it's 8 in the subsequent orbital. And how an atom reacts is going to be determined by those valence electrons. So sometimes it's going to be easier if there's only 1 or 2 valence electrons in, say, the second orbital. It may be easier for an atom to release those electrons, and then they have the underlying shell which is full. And that would be considered a happy orbital, a happy atom, and a stable atom. If an atom has, say, 5 electrons in a valence shell, it's not going to be very likely that it's going to give up all of those 5 electrons. It's going to want to gain 3 electrons. So keep that philosophy in mind as we move through the next slides, because atoms really want to fill up their shell. How they do it is going to be different depending on how many valence electrons they have, but that is the overall goal. They want to fill up a shell so that they can become more stable. So here's another image just overviewing some of the concepts that I mentioned in the slide before. So if we take a look at the atomic nucleus here, we remember that it's filled with the protons and the neutrons. And then this image illustrates the orbitals that exist around that. So we've got the first orbital, which is that first orange semicircle, and that would correspond to the first shell, lowest energy level, and there would only be room for 2 electrons there. The second shell is considered to be a little bit higher energy level. So if an electron is jumping from the first to second shell, there has to be a lot of energy absorbed in order for it to do so. The third shell is the highest energy level, and once again, it still only has room for 8 electrons, but those electrons would have a very high energy state. When an electron is potentially jumping down between the orbitals, that would be followed with a release of energy, because energy would have to be lost in order for it to go from a higher to a lower energy state. So this slide goes over electron shell diagrams. So these are important in illustrating the overall arrangement of the nucleus, protons and neutrons, as well as the electrons in space. So a few important things to note is that as we move down a column, so orient yourself with hydrogen here, followed by lithium and followed by sodium. Hydrogen is considered to be the smallest element because it only has one orbital. It also only has one electron in that orbital. If you take a look at lithium, which is the next element down in that column, it too only has one valence electron, so one electron in the outermost shell, but you will see that the underlying shell orbital is full. So there's two little electrons that completely surround the nucleus. So now we have the first orbital that is full, and we have one electron in the second orbital. Sodium has another full shell underneath, but you can still see that it only has one valence electron. So the nucleus is represented by the gray circle. You have 2 electrons in the first orbital. You then have 8 electrons in the second orbital. So that shell is considered to be full as well as the first one. And in the third orbital, once again, you only have one lone electron, valence electron. If you move along, so from left to right on the periodic table, you will also notice a few trends. As you move left to right, you are simply adding an electron to that atom to form another one. So lithium, you can see, has one valence electron and then 2 electrons in the first shell. Beryllium has a similar configuration, but all you're doing is adding an electron to that valence shell. So now we have 2 electrons in the outermost shell. Boron has 3, carbon has 4, nitrogen has 5, so on and so forth. So that gives you a bit of a background as to how these elements are arranged on the periodic table and what that actually means. When you take a look at the periodic table as well, and you look at an element, you will see 2 common numbers. The number on the top refers to the atomic number. So if you take a look at the yellow highlighted example of helium, helium has an atomic number of 2. Helium also has an atomic number, which is down below the element symbol, and the relative atomic mass sits at about 4. So remember, atomic mass or atomic number refers to the number of protons. So we automatically know that helium has an atomic number of 2, so it contains 2 protons. Helium also has an atomic number of 4, which means that the number of neutrons would be 4 minus 2. So helium has 2 protons and 2 neutrons, and that is what we gain from that information. Keep in mind that helium is not charged at all. It's not an ion. So that means that its charge is neutral. So that means we can also figure out how many electrons are in that element. If an element is neutral, and if it has 2 protons, that means that it has 2 positive charges. As a result, in order to be neutral, it would have to have 2 negative charges, and that corresponds to 2 electrons. If you take a look at the resulting configuration of helium, you will see in the nucleus, you would have had, once again, 2 protons and 2 neutrons. And there you can see the 2 electrons orbiting around in the first orbital. Another important thing to note is, in the case of helium, neon, and argon, I'd like you to look at the valence shell. Every single valence shell of that element is considered to be full. These are considered to be your noble gases and your most stable elements. And they are stable because they have a full valence shell, they're not reactive, they're full, they're happy. There's no reason for them to give up or gain electrons or even want to do so. So they are considered to be the most stable elements.